Greetings and welcome, friends. We've been talking about angles and radian measure. Looking at the page 348 on our homework, we're starting with problem 29. And they asked us to evaluate this expression. So they want us to figure out what tan of 7 pi over 6 is. Now notice that 7 pi over 6 does not have a degree symbol attached to it. They're talking about radians. All right, and now technically I know we might have the ability to convert from, degree to radian, radian to degree. But I'm going to first try to do this entire problem within the world of radians. Here we are. So I'm going to actually draw a little picture. I find they're always helpful. I'll draw it over here. So we can kind of figure out what this angle is. So first of all, 7 pi over 6 in terms of radians. Is that bigger than 1 radian or smaller than 1 radian? Or sorry, pi radians, my bad. Bigger than pi radians, right? And pi radians would have been a full kind of 180 degrees is what we'd be talking about there. So it's bigger than pi radians by 1 pi over 6, right? Because 6 pi over 6 would have been pi, and 7 pi over 6 is a little bit bigger. So it's looking like it'd be something like this here, where this angle is 7 pi over 6 radians, right? Now, what would the measure of the reference angle be here in radians? Right? Pi over 6. 1 pi over 6 radians, right? Okay? And now let's consider also, regarding tangent, which quadrants it is positive in. And this one's the trickier one, perhaps. It's positive in the quadrants that sine and cosine agree in. So for instance, quadrant 1, sine and cosine are both positive, so tangent is positive. In quadrant 3, sine and cosine are both negative, and a negative divided by a negative is positive because tangent is the ratio of sine to cosine. So this is positive here, and it's negative in these remaining quadrants. So what that tells me is that tan of 7 pi over 6, that's the same as the positive tan of plain old pi over 6. All right? And tan of pi over 6, I can actually do my hand trick for. Let's see if I can figure this out here. Oh, jumbo hand right there. So let's see if I can figure out my fingers. So here's my 0 pi finger, or 0 degrees. Here's my pi over 6 finger, or 30 degrees, which that's the one I'm looking for, but I'm just going to give us practice with our fingers here. Here would be my pi over 4 finger, or 45 degrees. This would be pi over 3, or 60 degrees, and this would be pi over 2, or 90 degrees, all right? Just so we're aware of that. So I would put my pi over 6 finger down, and tangent is the ratio of the square root of the fingers to the left divided by the square root of the fingers to the right. So it's going to be the square root of 1 over the square root of 3 is what I'd be looking at, which is 1 over the square root of 3. Or that's the same as rad 3 over 3. And that is what the book also says. So we have some degree of concurrence here. Welcome back, my friend. So that is problem 29. Now what I want to point out is if I wanted to convert 7 pi over 6 to degrees instead of radians, all right, what I could do, all right, 7 pi over 6 radians, do you guys remember how I'd convert it? What would I multiply this by? To convert to degrees. Well, it's actually the 180 over pi. And the way I usually remember, and this is probably a technique that would get you there 90% of the time, radians typically have the pi written within it. So I'd want to multiply this by something that would cancel out with that pi. So the pi would have to be on the bottom in order to cancel out with it. So that's how I kind of remember that. But usually you can kind of think about it and try to figure it out using other ways as well. So let's see, if I multiply across here, the pi's cancel out, as I said a moment ago. 6 goes into 180 30 times, and I'd have 7 times 30 left over, so that's going to be the same as 210 degrees. All right, which is what we were talking about here, right? So 210 degrees, and the reference angle would have been 30 degrees, if you wanted to think about it like that. So 210 degrees or a 30-degree reference angle, right? Just so I want you to have that association between radians and degrees. I think that's helpful, but I also would like you to at some point be able to fully rely on radians as well and not always have to convert back to degrees. And I'm sure your calculus teachers would appreciate that as well. So let's see, let's look at another problem here. It says, given the measurement of a central angle, find the length of its intercepted arc in a circle, all right, of radius 14 centimeters, round to the nearest tenth. Now, you might remember yesterday we had an arc length formula. Arc length was referred to as S. And what was the formula for arc length? Do you recall?
S equals R theta.
R times theta. All right, the radius, all right, which we've got there, multiplied by theta, but there's a problem with this theta here. This theta in the formula only works if we are measuring in radians. Okay, so my first problem here, or well, not problem, is I just have to convert my units. So 320 degrees, to convert that to radians, I would multiply by pi over 180. Actually, I'll write that in the yellow. Why not? Why not? Pi over 180. All right. So notice doing this would introduce a pi into the numerator, which is typically what our radians have. So that's how I like to remember my usual little layout there. So let's see, 180 and 320. Ooh, boy, what goes into both of those? Well, I could cancel off the zeros, first of all, dividing them both by 10. And now I've got 18 and 32. Is it? No, 6 doesn't go into it. 2, is it better than 2? Is there a better number than 2? 4 goes into 32, but yeah, I think just 2 goes into it. Yeah, so this goes into that 9 times and into 32. 2 goes into that 16, right? So it looks like this is going to be in radians. This would be 16 pi over 9 radians, right? So that's measured in radians. And with these radians, now I can calculate the arc length of that intercepted arc. So I'm going to plug that in for theta. And I'll get S is equal to R is 14, as we said a moment ago, multiplied by the 16 pi over 9. 14 and 9 cannot cancel out, but 14 times 16, we've got 224 pi over 9 is our measurement. So this is an arc length, and this would be measured in centimeters, specifically, agreeing with the units of measure of the radius. So, so what we had here, 16 pi over 9. Question, is that bigger than pi radians?
Yep.
Yep. Oh man, that was a sad circle right there. Yeah, it's bigger than pi. Is it bigger than 2 pi radians? No. I know that because 2 pi radians would have been 18 ninths, right? Pi, right? So it's less than that. So it would have been somewhere over here, and the arc length that I'm talking about would have been this whole yellow distance curve. All right. So the distance around this whole thing would have been 224 pi divided by 9, which I could get a decimal approximation of that, which is going to be 78.19 centimeters. All right, so this radius was 14 centimeters, and this distance around this far is 78.19 centimeters is the idea. All right. So we can actually find the length around a, semicircle of really any angle that I'm talking about. In this case, our angle was the 320 degrees, right? So this was a 40-degree reference angle, I guess, if that mattered to us, which it didn't in this case. And the thing I just wanted to point out is that theta only works in this formula if your angle is measured in radians. All right. Now, technically, if we wanted, I could make a formula for arc length according to degrees. What would that end up looking like? What did I have to do here to get?
Just be times 180 over pi.
Yeah, I could just have r theta pi all over 180. All right. So this would be a degree form versus radian. All right, so I would just have to include the part of converting it to radians built within the formula. But it's not as elegant of a formula, that's all. It's not quite so elegant. All right, last quick question. Here we are. It says the arc is 70.7 meters long. So I'm going to call that S equals 70.7 meters, and is intercepted by a central angle of 5.4 radians, or 5 pi over 4 radians. Silly me. Salami. Let's see, radians, right? Find the diameter of the circle. All right, so, well, what I can do is, if S is equal to r theta, I'm going to find r and then double it to find the diameter, is really the idea of what I'm going to do here. So for this one, I'll have 70.7 equals r times 5 pi over 4. So to solve for r, I would multiply by the reciprocal of this on both sides, I suppose. So 4 over 5 pi on both sides, right? And I'll end up getting r equals, let's see, 70.7 multiplied by 4 divided by 5 divided by pi. Notice I did double divide. I also could have divided by, in parentheses, 5 pi in my calculator, and that would work as well. And I get r is equal to 18.0036. So if I want the diameter, I would just double that, right? And that's where I'd get 36.0072 meters. All right, so you can use this technique to kind of work backwards and stuff too. So I imagine finding arc length can be helpful for different purposes. I mean, finding a portion of a circumference around an object, right? Like for instance, if you were designing a track and field track, and you want to figure out, you want this distance around the track to equal 1 mile, you could kind of do some work and figure out how far is this arc, which, arguably you could just combine, this portion and this portion and get a full circle and find that circumference. But, I don't know, you could find, different things like that, or I guess well, they do sometimes run only a portion of the way. I don't know how many meters that is or whatever they do. Yeah. So they do different things like that sometimes too. So you could use this as a tool for all sorts of calculations. But all right, friends, thanks for watching. Have a great day. Bye-bye.